So here, and for k label, it's n equal to 1. L label, n equal to 2. And the m label, it means that n equal to 3, n label, n equal to 4. And so if you have a knock out 1s electron, or you knock out electron from the k label, okay, then when the X-ray, the other label electron come back to fill in the k label, so it will give out X-ray, and then we name this as k alpha. So n equal to 2 to n equal to 1, this give out a k alpha line. And if m to l to k, we call it a k beta. And if n to k, we call it here m to k is k beta, l to k is k alpha. And you can also have m to l, and we name this L alpha, and n to l, we name it L beta. And for the absorption, that means you excite the electron from k label to any label, you can use this EK and ABS. And here absorption, that means that the knockout electron kinetic energy should be the your instant photon minus your absorption energy. Let's take an example of copper atoms. Quite often you doing the copper radiation in in-house X-ray machine. And in such case, quite often we have K alpha 1, K alpha 2, K beta 1. And if you look, now we look closer at this picture. And for K level, actually it's you create a cohort in 1s. And L, you have K, L, M, N. For L level, you can have a sub-level, L1, L2, L3. Or you can write down it as 2s, 2p 1/2, 2p 3/2. And for the copper K alpha 1 radiation, that means this is from the L3 and 2K level. And for copper K alpha 2, it's from L2 to K. And for copper K beta 1, it's from M to K. And K beta 3 is M to K here. Now this M is M2 to K level. Okay, now we're talking about transition probability. And because you excite electron, and you give the electron will transition to any state. And to understand this phenomenon, there's one we call it a Fermi golden rule. And this golden rule we're using the time-dependent perturbation theory. And you can obtain the absorption probability. And the absorption probability mu E is proportional to the square of this term. Here you have initial wave function. Okay, we say it's the initial state wave function psi I, and psi F means the final state wave function. And this epsilon, it means the X-ray electric polarization here, and K vector here is the X-ray electric wave vector. So your transition probability is proportional to this one. Here is epsilon times your R dot R, and there's exponential IK dot R. And this could be approximate like this one. So you this term be deconvolute to one dipole and one quadrupole term. Here the dipole term you only have the electric polarization times your direction vector dot r. And the other term is a quadrupole term. And in the dipole approximation, here the exponential term actually is neglect, and the absorption probability is independent of the direction of propagation of the X-ray. Okay, because the K vector already skipped. So, and it only depends on the relative orientation of the sample axis with respect to the epsilon. That means the electric polarization of your X-ray. And when we want to interpret the near edge spectrum, at the beginning we use the dipole approximation. And for those we cannot understand phenomena, we will include the quadrupole term. Okay. With this dipole approximation, and once you put the wave function, for example, you put a hydrogen wave function, you have radial part, angular part, and then you can finally, because you want to this transition probability is not equal to 0, so you can get the selection rule. So the consequence of dipole approximation selection rules will be like this. Delta L, that means your initial state and the final state, the difference, the angular momentum difference, or the delta L, the is equal to minus or plus or minus 1. And the delta S is a spin quantum number. Delta S must equal to 0. And the delta J is plus minus 1. And delta M is 0. And so for one electron transition, and if we are talking about a KH or L1H, KH means the electron is from you knock out electron from 1s orbital. And L1 means you knock out electron from 2s. And so your initial state is S, L equal to 0. And your final state is according to the selection rule. So the allowed transition should be L equal to 1, or so it should be a P state. And for the H at L2 and L3, L2 that means it's 2p 1/2. L3 is 2p 3/2. And your initial state L equal to 1, and the final state could be S equal to 0 or L equal to 2. That means D state or D orbital. Okay. With such a selection rule, now let's look at this picture. The horizontal is instant photon energy, and the vertical is a normalized absorption coefficient. And then this is a general X-ray absorption spectroscopy. And just starting from here, and at the beginning, you can see that there's a small peak, a weak intensity small peak here. And in this region, quite often we call this small peak as pre-age. Just before this, you see there's a rising age here. This is a rising age. Your intensity go up quickly, and before this, you have the small peak, where we call this pre-age. And this pre-age quite often is related to 1s to ND transition. And if we think this is 1s, you knock out 1s electron. And in principle, according to dipole selection rule, this is allowed transition. So this one should be this rising edge. This we call it white line. It should be 1s to n plus 1 p state. That means according to selection rule, should be 1s2 p state. But before this, you find a small intensity peak, and this weak intensity peak, quite often we interpret this as a 1s2 d state, and because it should be forbidden, so that the intensity will be weak. And once when you increase your photon energy, so that the electron can be knocked out and go to the continuum state. And once the 1s electron go to the continuum state, and you can consider it's a free electron, and you can also consider it's a wave. And this electron can interact. The wave can propagate out, and you become like you have outgoing wave, and there's some atom neighbor your atoms, absorbing atom. So there's a backscattering, could have a backscattering wave, so that you can find to the end you get such modulation, or you can see such oscillation feature in your spectrum. And we consider such like this. This can consider like a destructive or constructive interference between your absorbing atom. You can consider the outgoing wave and the backscattering wave. And for once the electron knock out to the continuum state, and it will interact with other your neighbors atoms, then this will give out we call it extended X-ray absorption fine structure. We name this XAPS. Now we look at this region, this white line, and okay, this white line, the intensity of this white line actually it depends on the matrix elements and the occupancy of any bound final states. And the matrix element depends on overlap between the wave function, and this means related to the distance between atoms. And this here, the distance means you have absorbing atoms and the other atoms nearby this absorbing atom. This distance means this. And the transition are forbidden into field orbital, because you want to excite already occupied electron to other state. So the intensity should be if the state is already filled, then the electron cannot go to that state. So the transition are forbidden into field orbitals. And the last one is the filling of orbitals will suppress the white light. So if the orbital already have some electron, the white light, your intensity should be decreased. And the other one we have to remember is for such kind of process, your instant photon energy actually it knock out for example, it knock out one s electron. That means it create a cohort. So the cohort lifetime will really influence your spectrum. And here the cohort, it's a vacancy in the initial state following X-ray absorption. It's unstable. It decays in a very short time, within 1 femtosecond, typically by emitting a fluorescence photon or OJ electron. And according to uncertainty principle, the energy width of a state is inversely proportional to its lifetime.